3. Today's gonna be another combo lesson, so it's lesson 3 and 4. That should be the last one of the unit. The rest will be like singular lessons. You just need time to like quiz and spend more time on like the more challenging stuff. I don't think today's is that challenging, so that's why we combine them. So that probably means there'll probably be almost a whole hour that we spend doing the lessons and the activities. That means on your own time, you have to do the homework, which is not long at all. All right, I still split up the homework into lesson 3 and lesson 4 so that you know what lesson you might need more help on. But there are like 4 questions and 5 questions. Like they're super short. So please do them. If you have questions, let me know. Come to tutoring. There is Saturday Academy this Saturday. And what I noticed is that the kids that I invited, like specifically because they were failing, did leaps and bounds better on their retake most recently. Okay, I recommend that for everyone, not just kids that are failing. It's a great opportunity for tutoring on a Saturday. I will be there this Saturday. I don't really go much often to them because I don't usually have time, but I have time. So I'll be there if you need extra help for 3 hours. All right. Anyway, your task from the warm-up is to tell me what each percentage means based on the real life situation. So table 7, can you tell me what the 10% represents? 10% of what? I'll give you 3 minutes to go over 3 of them. You don't have the first one. We'll come back to you. Table 8, 67%. So tell me about the 67%. 67% of what?
I was really right-handed people.
So of the right-handed people, 67% prefer pie. So let's see. There's only one 180 in the table. There's only one 270. So are we talking about of the right-handed people? Does that make sense? So out of the 270, is that referring to right-handed people total? Okay, so that so far is making sense. And does the 180 refer to right-handed people that prefer pie? Yes. So then that is correct. Good. So of only the people that are right-handed, 67%, which is the math they did to get 67%, prefer pie. Not 67% of people that were surveyed are right-handed and prefer pie. Just the right-handed people, 67% prefer pie. Questions on that? So really on the test, I don't know if they'll have you be working backwards like this, but the question will be like, what percent of right-handed people prefer pie? And then your answer would be 67%. You have to know what 2 things to divide to make it make sense. All right, so then table 7, back to you. 10% of what? So of left-handed people prefer cake, is that, did I do you right? Yeah. Okay, so let's see if that's true. So there's 110, there's 100. Class, is the 100 referring to the total of left-handed people? It's referring to the total of. So really those 2 phrases should be flip-flopped. So instead of the left-handed people, we're going to say the people who prefer cake 10% are left-handed. That makes more sense. So out of the people that prefer cake, 10% of them are left-handed. 90% of them are right-handed. And that's out of the people that prefer cake. Make sense? Usually what follows of is what you divide by. Right? So let's see that pattern. Table 1. What about the 30%? 30% of what? What is the 30% referring to? Okay, so we're saying 30% of right-handed people prefer cake. I would say of people surveyed are right-handed people that prefer cake. Does that make sense? See the difference? Yeah, because look at what they divided by. 300. 300 is the total that was surveyed, because it's in the bottom right, that intersects the row total and the column totals. So of all the people surveyed, 30% are right-handed people that prefer cake. So are right-handed and prefer cake. All right, not out of just the right-handed people, not out of just the people that prefer cake, out of everyone that was surveyed. Questions on that? Okay, so that helps you with some questions on your test. Hopefully, you know what to divide by. It's usually what it's out of. So what's all in is usually what you have to divide by. Now moving on. The first lesson today, lesson 3, is about association. So association, another word for that would be relationship, correlation, I use more frequently. We're going to look at the two variables that are being compared and see if there's a relationship or an association. So for example, if I go back to the warm-up, where we compared dessert preference to like left or right-handed dominance. Do you think that if you're left-handed or right-handed, you prefer a certain dessert more? Do you think that those are related? All right, now, I don't think that those are related either, but some people might see this data and think otherwise. All right, like if something increases while something else increases, then people make certain assumptions because there's an association between them. Or when something increases and something else decreases, same thing. They might think that they're related. Doesn't mean that they actually caused it, so that's like a different day that we'll talk about causation. But if there's a correlation, you'll see kind of like a pattern. And that's what we'll see today. So, first example that is on your notes. Can someone read it for me? My voice, I'm going to try to save for this hour at least. So, someone read this one for me. All right, go ahead, Harvey.
They first look at how likely might be able to correlate with the response to hold forward of your own penetration lower relatively insensible for the data
Okay, perfect. Thank you. So if you're not really like familiar with oral health and blah, 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 that's fine. You just have to see. These are the two things being compared. And it might be hard to distinguish relationships when it's just in a two-way table, which is why we might want a relative frequency table that tells us, like, in proportion, how much something occurred compared to something else. So you have a partially filled out table on your paper. You're going to fill in the rest. And you're doing it based off of the total for each column. You guys know the difference between a column and a row? What way do columns go? Wait, show me again. Up and down. And then rows go like left to right, right? So when we say total for each column, we're talking about these totals. These are my column totals. So the way that they got this relative frequency of 100% here, they did 28 divided by 28, got a decimal, timed it by 100%, and it's 100%. This one, they divided 27 by 27, and that's how they got 100%. You guys need to divide by the respective column total what numbers are in the other table. Does that make sense? So what am I dividing for this top left box? Not by 100%. By 28. And then you get a decimal, then you times by 100%, and then you tell me what percent that is. And do the same for the other three boxes, but for the correct column total. Questions on that? Okay, we don't want to spend forever on this, so I'm gonna give you 1 minute, because literally it's just division and you use a calendar. Let's see, does anyone still alive for the restroom? All right, go ahead. Yeah. 8. Then I put that in my calculator, I get a long decimal. And usually it'll specify what to round to. Let's just round to like a whole percent. But as long as you know your rounding rules, hopefully like you just keep it consistent. But yeah, when I times that decimal by 100 to get my percent, what percentage should you have gotten? Oh yeah. Good, 71.4%. Because remember, you're supposed to divide 20 divided by 28. We even told you. Remember? 20 divided by 28. You take what was in the 2A table divided by its column total. So in that same column, my unhealthy coral was 8. Divide that by 28. You get a decimal. And then times that by 100%. Table 2, what percent would that be? For this one, not my mouse is on. Is 29%, good. And this should add up to 100%. And that's only because we're doing it by the column total, so then your column should add up to 100%. Questions on that? Okay. Table 3, what percent did you get from the top right? Okay, table 3, we'll come back to you. Table 4, this middle right, what'd you get? Okay, good. I'm gonna round to the 1%. Let me check. So there's two things I need to divide are 22 divided by 27. and then times by 100%. If I'm rounding to the whole percent, I get 81% right here. So then table 3, what goes right here? %. One, because we found the other one. So then it's just 100% minus 81% is 19%. And 2, because that math that you would have done would have been 5 divided by 27 for this one. If you need to show the word somewhere or in the box, go ahead. But it was 5 divided by 27. You get a long decimal when you do that. And that's about 0.185. When you times by 100%, that's about 19% rounded. Questions on that? Okay, so relative frequency tables. Now, what this does is it helps me see, okay, when I have low nitrate concentration, so read the table, follow along, low nitrate concentration, which one has a higher relative frequency, healthy or unhealthy coral? Healthy. Are we understanding the question now? There are 2 options, healthy or unhealthy, which has a higher relative frequency when it's low nitrate concentration. It would be that one, the healthy one. When it's high nitrate concentration, which relative frequency is higher, healthy or unhealthy? Unhealthy. So that answer is B and C. When it's low nitrate, we have more healthy coral. When it's high nitrate, we have more unhealthy coral. So do you think that there's a relationship between that? Yes. Why, Uli? Good. So your explanation is good. You could put that on a test and get the full point. You could also say because as nitrate increases, and I'm summarizing, really it's like nitrate concentration, but as nitrate increases, healthy coral decreases. So noticing that could mean that, yeah, there's probably a relationship between the two, or an association, a correlation. Questions on that? All right, so now we're on this part E. We have a new table for you. The scientists look at how silicon dioxide concentration might be related to coral health. And here's the relative frequency. So you don't have to calculate it this time, they already provided them, bless you. Based on this data, is there a possible association? Don't answer out loud yet, but look at it, it's also on your tape, it's also on your paper. Do you think that there's a possible association between silicon dioxide levels and healthy or unhealthy coral? Take a minute, talk about it in your group, explain your justification, and then I'll call on someone at random, so make sure you're all participating. Part B. I think that there is an association based on these numbers. Raise your hand if you think there is not an association. Okay. Frankie, why do you think that? So no, because Wait, Bowen help her out? No, because
No, because there's not really much of a change. Maybe it's 3%.
no, because there is not much of a change. As silicone dioxide increases. Something to that effect. Notice like the numbers are slightly different, like by 2%, but like that doesn't suggest that the silicone dioxide caused it, maybe something else did. Nothing really changed. So that could be another reason why you see there's no association. It says there's not much of a difference. You can't see a pattern, like you don't see that as one increases, the other one's decreasing, or as one is increasing, the other one's increasing, nothing like that. All right, so good on lesson 3. Do you think you can determine association between variables based on data? Okay, well, there's practice for you in your Schoology, not saying like do it right now, I'm saying like when you do it later, if you're not seeing a trend from just the numbers, make a relative frequency table like you just did right now. Okay, and then it'll be easier to see if there's a trend or not. But we're gonna move on to lesson 4, which is about linear models, my favorite. And I'm not being sarcastic, like it's genuinely my favorite. I feel like it's the most real world applicable. If you plan to do any sort of STEM field, like nursing, pre-med, I have a degree in forensic science, so anything like science related where you have to take chemistry, biology in college. I know business has a lot of math, so maybe even that field as well, you'll have to know this. But literally every single lab that we ever did in college was us gathering data, putting it in a computer to make a scatter plot, typing in a code to get this equation, and then using that equation to like predict other stuff or to see how good our data is, like over and over and over again. So this is going to be like your life for the next 8 years if you decide to go that route. I think it's easy. So here it is. Here's an example of a linear model. Tell me a few things you noticed. I'm not even going to give you a whole lot of time to think about it. Just raise your hand. What's something you noticed about this? There's lines and dots. Harley? So the dots kind of follow the pattern of the line. No? Okay, so about the same amount of dots. I'll put approximately. So approximately same amount of dots on each side of the line. That's a good observation. You'll see why in a little bit. And anything else we noticed? Is the format of this formula something we recognize? We just finished a whole unit centered around that formula. What format is that in? Y equals mx plus b, which gives you straight lines when you graph them. So here it is again. So good notices. We don't really have time for wonders. I'm sure you're wondering a lot. Like, what is this graph for? Why do we care? Something, I don't know, but let's move on. So here's an example of a linear model. First thing, we're gonna practice gathering data. So I'm gonna play a video for you. And as I'm playing the video, it's gonna be someone putting oranges in a box. There will already be like, I think 2 oranges in there, or 3, I don't remember. But you're gonna look at the scale and write down what the weight is. Okay, so you're gathering data. As every time they put an orange in, you're writing down the weight that's on the scale. I'll try to help you out, like if you're, super far and you can't see the scale, but like here's the number. But don't worry, I'll share the values with you if you miss one, but just try to collect it yourself. See how close you are. All right, so there's 3 oranges already. That way 1.027. Adding another one. Do I need to pause? Okay, now we're at 5 oranges. That's how much it weighs. Actually, adjust what the 5 oranges is to the 1.502. Sorry, I should have waited for the scale to like level out. Okay, now there's a 6th orange. That's the weight. 1.617. Seven oranges. That's the weight. Now there's 8 oranges. Nine oranges. And oranges. Looks like it leveled out there. And is that all? Okay, let's see. I do have it in my table. I'll rewrite it down. What are we on lesson 4? Sorry, give me 1 second. Okay, so in case you missed any, here's what the book says. Hopefully the book has it really lined up to what the video was. All right, so that's our table. So I can tell you later on, once we make our linear model, we're going to be estimating like how much 11 oranges would weigh or 50 oranges would weigh. Like we're not gonna sit there and put 50 oranges in the same old little box to see how much they weigh. We're gonna use our linear model to do that for us and or for any value you want. All right, but here's just like our raw data. Questions on that? Okay, so now you're gonna use that data and you're gonna make a scatter plot. So, oops, I didn't want to show you the linear model yet. Let me erase it. But use your table to make a scatter plot. It's like coordinates. So we can make the number of oranges X, because that's independent and it'll go on your X axis. And the weight Y, because that depends on the number of oranges. That should go on the Y axis. So then, just like you would graph on a coordinate plane, your first point will be where 3, 1.027 is approximately. Put that on your scatter plot. I'll freeze it and do it at the same time, and we'll compare. Hopefully you know how to put that on the coordinate plane. So I'm gonna do that. All right, I just finished plotting all the points, so that means you get like 10 more seconds. All right, so using our data, I made a scatter plot. Yours should look similar. And of course, it's hard when there's no grid lines, but they should be in approximately zone areas. Each tick mark, although they're not all labeled, goes up 0.25. So like here's 2.25, 2.75, all that stuff. Questions on how to fill in a scatter plot? Okay, now to make our linear model, which is something you'll have to do by hand and on your constructed response, you want to draw a line through the data that fits the data well. And there's some like criteria for that. If it fits the data well, we want it to go through the middle of our data and where all the points seem to be clustered around. So we don't want our line to be like above all the data points, below all the data points. We want it to go through the middle of our data. Is it important that it touches all the data points? It's not. It just has to be a straight line through the middle of the data where all the points seem to be clustered around it. Sometimes not even any of them touch the line. It just depends. But like for you, especially when you take your test, I suggest like get another piece of paper and like line it up to where you find like your middle and then draw the line straight as possible. All right, I'm going to use my little line tool. So that's what you should do. Is like line it up, draw a line as straight as possible. Something like that. Through the middle of the data, where all the data seems to be clustered around it. It does touch some of the data points, but not all of them are perfectly on the line, and that's okay. But now, in order to make our linear model, which is in the form y equals mx plus b, we need to figure out a value for the slope and y-intercept. We're going to estimate it. So in y equals mx plus b, what letter is for slope? No. M is for slope. You guys don't know that? Again, that's something else you can make a flashcard about. But we need to estimate the slope. Okay, now don't just look at it and be like, oh, I think it's this. Because look at what our rise is. It's not changing by like ones, so you don't want to do that. What you should do when you're estimating your slope is pick two areas on the line. They do not have to be the data point, but that you can see really clearly without having to estimate a whole lot. So like, for example, let's see, I can see like right here is not a data point, but I can estimate that coordinate pretty well. The x looks like it's 1. The y is past the 0.75 mark, so maybe like 0.8, I'm not really sure. But you're picking two coordinates on the line that you can see clearly. Again, it does not have to be a data point. Can someone tell me one more coordinate that they can see pretty well? Maybe on your paper too. But it needs to be from the line. All right. right, bending. So tell me a coordinate from the black line that I drew that you can see pretty well without having to do like a lot of estimating. 2.5 and 10. So 2.5 and 10 would not even be on this road. Okay, so you need 10, 2.5?
Yeah.
Okay. So let's see. 10, 2.5 exactly. Are you referring more to the data point? Like that red dot? That one's like a little bit above the line, we want on the line. Let me try again.
9.
Okay, so near where that data point is. So yeah, we want data points, or I mean, they don't have to be data points, but we want the coordinates to be on the line that we don't have to estimate a whole lot. So yeah, that one's pretty good. Is it 2.2? Yeah, it's pretty good. So then you have your two coordinates. Here is a formula for slope to find the m that you need to memorize. So go ahead and write it down. Under number 4, probably. It's gonna be m equals y2 minus y1 over x2 minus xy. I know you're used to like rise over run, and that sometimes works if it's a graph that like the axes are labeled really nicely, but this one's not. So when you have coordinates, and that was your job, was to pick two coordinates from the line, you can use this formula. And again, even if you don't go to college, you will use this formula in every math class moving forward. It's rate of change as well, which slope is a rate of change. So pick one of your coordinates to be x1, y1, the other one to be x2, y2, and then put it into your formula and calculate your slope. I'll do that, but I'll freeze the screen. I want to see that you know how to plug things into a formula and use a calculator to get a value. So please do that. And we'll see if you did it right. Okay, so I finished calculating it. That means you should be not far off. Should have at least plugged it into the formula. We labeled all the parts. We gave you the formula. You got things in the formula. And then use your calculator to actually get the slope. And if you did it correctly, the slope should be 0.18 or 0.175 if you use the whole decimal. All right, so the way I labeled it, my y2 is 2.2, my y1 is 0.8, it's y2 minus y1. Then over x2 minus x1, 9 minus 1. I get these values, which then I need to divide, and that's how I get 0.18 for my slope. Questions on that? And that's what you'll do as well in the future, moving forward. Rewrite the formula until you have it memorized. Now for number 5, we're going to estimate the vertical intercept, or y-intercept, because that's the other part that is usually filled in by a number in our linear models. What letter is for y-intercept? B, thanks. Say it like louder and louder next time, but yes. B is your y-intercept. If you don't know it, star it, highlight it, you run with it. And look, our line actually touches the y-intercept. Normally, we do some math to figure out your y-intercept, but I can just kind of eyeball it. Where do you think it touches on the y? Table 3, can you tell me? About where is that touching on the y-axis? Gonna have to do any math for it, because you'll have to look at it. Is it touching that 0.9? Class? Okay, you know that because it's not right next to the 1. It's in between what 2 tick marks? It's between 0.5 and 0.75. So, and where it's at right now, what number would you estimate that to be? Not 0.06, it's 0.6. Yeah, but yeah, that's a good estimate. And then you put it all together. And you get a linear model. 0.18x plus 0.6. Now I can use this linear model to answer other questions that we maybe didn't, that we maybe didn't get in our experiment. So 0.18x plus 0.6. Questions on that? All right, I'm getting a little painful. Like, we need to be able, like, basically just test on it. Be able to identify a line of set approximately where it is. All right, depending on the values you used, we might have slightly different answers from each other. Like, there's no way all of you are going to pick the same exact 2 coordinates when you're working independently. So, like, in first hour, we had the same y-intercept, but our slope was 0.19. Isn't that pretty close to the slope that we have? For the love, is 0.19 close to 0.18? Like, I'm not asking you hard questions, I promise. Like, you just gotta answer them. Yes, it is pretty close. Answers were very slightly. But once you have your linear model, you can answer questions like number 6. If we have a box containing 11 oranges and we want to use our linear model to estimate the weight, where do I need to plug in that 11? For the X or for the Y? For the X. So please write that down. I know we might not have time to fully calculate it today. But in order to do that, all I have to do is type what's in the right side in my calculator. And then that will give me an estimate for when it's 11 oranges. What about if I want to estimate when it's 50 oranges? Where would I plug in the 50? When it's 50 oranges, where am I plugging in the 50? For the X, look, it's on the X-axis, number of oranges. If I wanted to figure out how many oranges there might be when the box weighs 20 kilograms, where would I plug in the 20? Not in the X. The X is number of oranges. I plug it in for Y, which is weight. That's why it's on the Y-axis. So that's another question you'll be asked on your test. Given this linear model, how many oranges do I have when the box weighs 20 kilograms? And that's how you do it. That's all you have to do. Plug in the all. All right. Now, last thing on our learning targets, which is on your paper, it's to interpret your slope and y-intercept in context of the linear model. So the slope, the 0.18. What does that mean? 0.18, what? Good. Every time we add an orange in, it's going up by 0.18 each time. That's what that means. That's how you can get some questions right on your test, is just telling me slope, which is always rate of change, what it means in this situation. Now the y-intercept. What does my y-intercept of 0.6 represent? It does represent 0.6 kilograms when what happens? When I have what?
Or
No oranges in the box. So the box still weighs something, and there's no oranges, it weighs 0.6. Easy questions on your test, honestly, in my opinion. You just have to make sense of what's going on. Why intercepts always your starting amount? Slope is always your rate of change. You have 9 questions for homework. Make sure you get them done on your own time. They're all based from the lessons. And don't lose your notes. You have time to put it properly in your binder folder instead of shoving it into it.